In this lesson, we are going to learn about a specific type of linear transformations called isomorphisms. Isomorphisms are basically linear transformation which have inverses. And when we say that a linear transformation has an inverse as a function, it meant to say that the linear transformation can be reversed or can be undone. So before we talk about isomorphisms, we need the following definitions. So we now define composition of linear transformations. So here you need two linear transformations L from V to W and another transformation T from W to U. Now I would like to illustrate this definition as follows, using this diagram. So here you get an L that goes from V to W, T goes from W to U, right? So if you have a vector v coming from little v, the image of it under L will fall inside or will be in the set W or in the space W. Now, L of v being in the domain of the function t, this t will now take L of v as an input and it will give you an output of the form t of L of v. Now, the function that takes v directly to t of L of v is what we call as the composition, t circle L. And that t circle L is going to be a map from v to u, and it's defined as the one that takes v to t of L of v. In other words, the composition t circle L simplifies the actions or summarizes the actions of these two linear transformations L and T. It can be verified that if L and T are linear, then their compositions, whenever possible, is also a linear transformation. You just verify, we just simply verify the fact, we just use the fact that both L and T are linear transformations. For example, if I apply T circle L on the sum, then I apply the definition of the composition. Because L is linear, I could write this as L of V1 plus L of V2. And also because T is linear, I could write this as T of L of V1 plus T of L of V2. Therefore, this is T circle L of V1 plus T circle L of V2. That proves the sum-preserving property of T circle L. Also, you can prove that T circle L of, let's say, AV equals A times T circle L of V. And that will complete the proof that the composition T circle L is also a linear transformation. To show you a good example, now let me have the following matrices A and B. Now we know that A and B are 2 by 2 matrices. They represent a particular linear transformation or a matrix transformation. In this case, matrix operator, because the size of the row and columns are equal. So it's a transformation from R2 to R2. They are transformations from R2 to R2, right? So we would like to sketch the image of the unit square with the following vertices under the composition TB circle TA. Now remember, the action of TA on these points is that we simply multiply the matrix A to each of these by writing this as columns. Okay? And take note that because we're considering a unit square, we only need to find out the images of the vertices as T is linear, as the transformations are linear. So here, remember, when you have a composition, the one that is acting first is the one that is on the right. So here, to apply TA to each of these points, I put here the A, the matrix A, and I put here the 4 points. I'm going to do these are the 4 points: 0, 0, 1, 0, 1, 1, and 0, 1. And then I'm going to perform matrix multiplication to get the images. So here, upon doing matrix multiplication, I saw that the image of 0, 0 is again 0, 0. The image of 1, 0 is 0, 1. The image of 1, 1 is minus 1, 1. The image of 0, 1 is now minus 1, 0. And I summarized it in the following table. So you can check it and try to graph the resulting image on your own. If you want to do it on your own, you might want to pause this video. Next, because this is a composition, after applying TA on the results, we apply TB. Right? Remember, because TB circle TA of V actually meant TB of TA of V. In other words, on these results, we now apply the transformation B. So here is the matrix B. Now here are the vectors, or here are the points corresponding to 0, 0, 0, 1, minus 1, 1, minus 1, 0. And then once again, I applied matrix multiplication to get the images, such, no? And I summarized the images as follows. So the final images will be these points with double primes, no? 0, 0, 0, minus 1, minus 1, minus 1, 0. So you are asked to sketch the image under the composition, right? So here I have a sketch. This is the original unit square. Instead of writing the coordinates of the vertices, I simply used colors for you to find out what will happen to them under the transformation. So in other words, these are the points P, Q, R, and S. After the transformation, TA has been applied. So you can see this is now P prime, Q prime, R prime, and S prime. What happened is that the transformation TA rotated the Cartesian plane at an angle of 90 degrees, causing this square to move like that, at an angle of 90 degrees. Right? That's why the blue point over here was sent over there. Right? And then we might want to apply TB on this result. So that's TB. And then we apply the final images of the vertices will be as follows. So what happens is that the yellow and the red that stayed at their places, the blue that went here, the green that went here. So TB, now as you can see, this is a rotation 90 degrees. Well, this TB in geometry is what we call as a mirror reflection about the x-axis. Right? And therefore, this being the final image, this would be the image of the original unit square under the composition TB circle, TA. If you're going to draw, let's say, let me place here, let me draw here an R. After applying TA, this R on the square will now be oriented as follows, because it will be rotated 90 degrees. Okay? Then after the mirror reflection has been done, this R will then be transformed into the following R, because it's being reflected about the x-axis. Okay? In general, if you have two matrices, A being of size M by P, and I'm sorry, I think I should have I think there's something wrong with how I write this. I think this should be M by P, and this should be P by N. I think I interchanged that. Yeah. Whenever you take the composition of two matrix transformation, the result is another matrix transformation, but this time the matrix is obtained by simply multiplying the old matrices. This can be seen easily by performing this or using the definition. So if you have a vector v, for example, or a vector x if you want, by definition this is tb of ta of x, right? Now ta of x equals a times x. Now tb of ax is now b times the product ax. Now because matrix multiplication is associative, this is equal to BAXO. It's as if we have just multiplied the product BA to x, therefore this is T BA of x. And therefore, the composition TB circle TA is equal to the transformation T time of BA. Now, we need to adjust this sizes requirements because we're multiplying B times A. So I was thinking of multiplying A and B, that's why the sizes are meant to be M by P and P by N. So I can multiply A times B. But actually, what we wanted to multiply is B times A, so the number of columns of B must coincide with the number of rows of A. Right? Okay. So there. So we are now defining what it meant for a transformation to be invertible. Invertible in simple words means that the transformation can be reversed, or the action of the transformation can be reversed. So you could recover everything in the pre-image stage whenever you know the image. For example, when you take a picture of a 3D object and transform it into a 2D picture, no? Now, all the features in the 3D are now transformed to a 2D plane, right? Take note that not every feature in the 3D, now if you just saw the picture, not every aspect of the 3D object can be recovered when you know, or when you see the picture or the image, right? Therefore, taking a photo is not an invertible transformation, for example. But some transformations are invertible. For example, if you rotate the plane 90 degrees above the origin, that's invertible because when you rotate an image 90 degrees above the origin, you could always undo that by rotating at an angle of negative 90 degrees. In other words, some transformations are invertible, some transformations are not. So what do we mean precisely when we say that a function or a linear transformation is invertible? It meant to say that there exists a linear transformation denoted by L inverse. This transformation goes from W to V in reverse of V to W of L, from V to W, such that this inverse does the following. When you take the composition of L inverse with L, what results is just the identity transformation operator on V. And when you take the composition L circle L inverse, you just get the identity transformation on W. So when you take compositions of two functions and the result is identity, that meant to say that applying L and then applying the inverse reverses everything. So nothing has been made really. And also, if that is the case, performing the inverse and after that performing L once again, that undoes the inverse. Therefore, nothing has changed in the space W. Now, in order to remember these equations, I have made these diagrams for you. No? So you can think about this as the L, and then L inverse is a function from W to V. The composition is now from V to V, so the result must be IDV if you want L inverse to reverse L. At the same time, if you want to remember this equation instead, no, L inverse is the transformation from W to V, and L is the transformation from V to W. So the composition L circle L inverse is IDW. So remember that the one on the right is being the one on the right is the first one to act whenever you get a composition. So the question really is that when is a function or when is a transformation invertible? This is a very hard question to ask because being invertible means the existence of something, right? So maybe there is a property that a linear transformation must have in order for that is easier to check so that we know in advance that it has an inverse or it is invertible. So what do you think is that property? Well, in earlier mathematics or in sets, no, we know that a function f from x to y, where x and y are plane sets, is invertible if and only if f is a bijection from x to y. This is one of the main theorems in mathematics that you should always remember. Here, the word bijection means the function is both one-to-one and onto. F being one-to-one meant to say that if you have 2 points in the domain, x1 and x2, and their images are actually equal, then it must follow that the points themselves must be equal. Or taken contrapositively, that means to say that if f is one-to-one, that means to say that two different things are mapped to two different things. On the other hand, when we say that f is onto, that meant to say that everything in the set y is used by f as an image of something from x. In other words, that meant to say that for every y in y, there must be something in x that are mapped, that is sent to y. Or more precisely, that meant to say that the direct image of x is precisely y. Sometimes the direct image or the range is smaller than y, but sometimes the range is equal to y. This is the range, right? And also, you must remember that if you have a bijection f from x to y, the inverse is also a bijection from y to x. For a linear transformation, L, from V to W, whenever a linear transformation is one-to-one, we have a fancy name for it. We call it a monomorphism. Okay? Whenever a linear transformation is onto, sabihin, the range is equal to W, it uses up all of W. We call it an epimorphism. And when a linear transformation is both one-to-one and onto, we call it an isomorphism. I know that in group theory, you have talked about isomorphism in abstract algebra before. But this time, sometimes whenever you talk about groups, whenever you talk about vector spaces in one situation, to distinguish this isomorphism from group isomorphism, you mention or you say L is a vector space isomorphism to be more precise. The following must follow from the previous discussion, no? That if L is an isomorphism, it has an inverse which is a function, and it turns out that the inverse is also an isomorphism because it's also a bijection, right? Here, to prove this, you only need to prove that the inverse is linear. When you say that the inverse is linear, mean to say that the inverse satisfies the two actions for linear transformation, and that is kind of easy to check. I'm leaving that to you as an exercise. Also, I want to say that the composition of two isomorphisms is also an isomorphism because the composition of two one-to-one functions is also one-to-one. The composition of two onto functions is also onto. Hence, a linear transformation L is an epimorphism if and only if the range or the image is exactly W. So in other words, the image of the transformation tells us when is a linear transformation onto or an epimorphism. So the real question is now, when is L 1 to 1? So if the range or the image tells us when L is onto or an epimorphism, it turned out that the kernel will tell us when is L 1 to 1. And this is what we call as the monomorphism test, because it tests when is a linear transformation a monomorphism. So here, L is a linear transformation from V to W. Then we can say that L is a monomorphism if and only if the kernel only has one thing in it. Now this condition means to say that the only thing sent to the 0 in W is the 0 in V, and nothing more than that. If you were able to show that the kernel only has one point in it, no, then that proves that L is 1 to 1, or L is a monomorphism for that matter. For the proof, we're proving, or we are first assuming that L is a monomorphism. So let V be in the kernel of L. Because we want to prove that the kernel only has the 0 vector in V, we wanted to show that this V is actually 0. How do we do that? First, because V is in the kernel of L, by definition of the kernel, the image of V under L will be 0W. But since L of 0V by default is also 0W, and L of V, then it follows that whenever this equation holds and this equation holds, yeah, you can compare, therefore L of V must equal L of 0V. Because L is 1 to 1, whenever L of V equals L of 0V, it must follow that V is the 0 vector. Proving that if you get something in the kernel, it's nothing but the 0, therefore the kernel can only have one element. Okay? So that proves 50% of the statement. So conversely, assume now that the kernel only has one element, which is the 0 element. Okay? So we now prove that L is 1 to 1 by selecting two elements in V and assuming that their images are equal. So to prove that L is 1 to 1, we just need to drop these L's. No, we need to show that V1 is V2. How do we do that? I will consider the image of their difference. And because L is linear, this translates to L of V1 minus L of V2. But because these are equal in W, then their difference is the 0 in W. And that will imply that this element V1 minus V2 being sent to 0 by L, that implies that the difference V1 minus V2 is in the kernel of L. But by assumption, the kernel only has one thing in it, the 0 vector. And that meant to say that V1 minus V2 is actually the 0 vector, and therefore V1 is equal to V2. This proves that L is a monomorphism. That completes the proof. So here, as an exercise, we're going to show that L is an isomorphism from R2 to R2. So given this formula, and find the formula for the inverse, right? So how do we do this? First, you first check that L is linear. You say L is linear, the two axioms for a linear transformation are satisfied, and I'm leaving this to you as an exercise. Okay? Next, you might want to know the kernel of this linear transformation. The kernel, if you want this to be an isomorphism, you want this to be both a monomorphism and an epimorphism. If you want this to be a monomorphism, you want the kernel to only have the 0 vector in it, right? And if you want this to be an epimorphism, you want the range or the image to be the entire R2. So I may just want to check for the kernel. No? The kernel of L, by definition, is the set of all points in R2 whose image is the zero vector in R2 as well, because this is a linear operator from R2 to R2. Okay? Therefore, xy is in the kernel if and only if Lxy is 0, if and only if x plus 2y, x plus y equals 0, 0. And this gives me a linear system. In fact, a homogeneous linear system. So here, we're going to solve this, right? We're going to solve this and show that the only solution is the trivial solution. Okay? Because that's what we want. We want x and y to be both 0. And when that happens, that meant to say that the transformation is a monomorphism. So we use Gauss-Jordan if you want, or you may want to use simple elimination. Okay? I'm going to do this. 1, 2, 0, 0, minus 1, 0. And then I'm going to multiply a negative 1 on the second row. There. And then I'm going to do this. So I have 1, 0, of course. Oh my gosh. So what happens is that x and y are both just 0. So therefore, the kernel only has one vector in it, namely the 0 vector. Therefore, L is 1 to 1. Or a monomorphism if you want to be fancy. Right? To prove that L is onto, take note that I don't really need to do anything more. Why? Thanks to the rank nullity theorem. Right? If I'm going to check, so note that here the nullity of L is 0 because the kernel only has one vector or one point in it. The dimension is 0. By the rank nullity theorem, what does the rank nullity theorem say? The rank of L is precisely 2 minus the nullity of L. 2 being the dimension of the domain. But the nullity is 0, so this is 2 minus 0 is 0. So the rank or the range is two-dimensional. Right? This means that the dimension of the image is two-dimensional. And since the image is inside R2, so the only two-dimensional subspace of R2 is R2 itself. Therefore, the image is R2. I don't need to check anymore because we already have the rank nullity theorem. Therefore, L is an isomorphism. Okay? Next, because that being an isomorphism, we want to find a formula for what? For L inverse of xy. How do we get a formula for L inverse of xy? So let me erase this board for you. Alright, so here we go. So suppose that L inverse of xy is, let's say, x prime, y prime. So here, we wanted to, so the goal is to express x prime and y prime in terms of x and y, because we want a formula for this inverse. So as you can see, if I apply L on both sides, right? If I apply L on both sides, the left-hand side will cancel, no? Right? That will cancel because L circle L inverse is the identity, right? But in this case, it doesn't matter which is space because the domain and the arrival space are the same. So it follows that L of x prime y prime equals x y. So that meant to say that x prime plus 2y prime comma x prime plus y prime equals xy. So what you want to do now is you want to solve this linear system. The unknowns being the x prime and the y prime. So I'm going to do this 1 2 x 1 1 y. So here the unknowns are x prime and y prime. So I'm going to use Gauss Jordan just like before. We did this before. Had I known, I have done this with the one before, but let's just redo everything. Okay, so I'm going to do this 1 2 x, that will not change, 0 negative 1, and then it will happen here. I will subtract y minus x. Next, I'm going to multiply the second row by negative 1, so I have 1 2 x 0 1 x minus y. Right? Next, I have to eliminate this. That's e 1 2 negative 2 1 0 this time. So that's a scratch. Let's work on a scratch over here. X minus 2 times x minus y. So that's what we wanted to do. X minus 2, x plus 2y. That's minus x plus 2y. Yeah, there. I hope I did that correctly. So if I made an error in the computation, you can tell me, or you can comment now if you want. Let me erase this scratch part. So there, we're done. This is for x prime, this is for y prime. Therefore, L inverse of xy is minus x plus 2y comma x minus y. Okay? If you want to check some examples, for example, you get let's say xy is 1 2. Okay, if I take the image of 1 2 under L, I use this formula. So x plus 2y becomes 5, x plus y is 3. Now if I apply L inverse using this formula, minus x plus 2y minus 5 plus 2 times 3 is 1, and x minus y is 2. So as you can see, I go back from 1 2 to 5 3 and then back to 1 2. If you apply L inverse first using this formula, you want to use that formula, that's minus x plus 2y minus 1 plus 4, that's 3. Then x minus y is negative 1. If I now apply L, you see if L will undo L inverse. L is x plus 2y, x plus y, x plus 2y 3, minus 2, that's 1, x plus y is 2. Alright, very well. So it worked for 1 2, and I hope that it will work for any xy. Right? Did you see the idea of the inverse? They undo. L and L inverse will undo one another if they are placed side by side. Now, You see, in the previous example, it turned out that because L is a linear operator, the dimension of the domain and the arrival space are equal. We can somehow generalize the previous example. If L is a linear transformation from V to W where V and W have the same dimensions, so they are both finite dimensional, the following are equivalent. Number 1, L is an isomorphism. Number 2, L is a monomorphism. Number 3, L is an epimorphism. So these three things do not really differ when the dimensions of V and W are the same. So in other words, the way we actually use this in linear algebra is using the following, no? So when you want to prove that L is an isomorphism, you found out that V and W have the same dimensions. You just need to choose. Either prove that L is a monomorphism, that's enough, or L is an epimorphism, that's enough. No? This corresponds to showing that the kernel only has this, and this corresponds to proving that the image is the entire W. So you will just select one. That is enough to prove that L is an isomorphism. To show why this is true, for example, the key ingredient here is the rank nullity theorem. For example, 1 already implies 2 by default because an isomorphism is both 1-to-1 and onto, therefore 1-to-1. The question is, why must 2 imply 1? The question, the trick is to use the rank nullity theorem. So if L is mono, no, that means to say that the kernel only has 0 vector in it, therefore the nullity of L is 0. Right? Why would it be an isomorphism? Because it is also onto. Because it's onto because by the rank nullity theorem, it's the dimension of so the rank is a dimension of V minus what? The nullity. And in this case, the nullity is 0, so the rank equals the dimension of V, and therefore the image is exactly, and by the way, the dimension of V equals the dimension of W, therefore the image of L is equal to W. That's it. Therefore, that proves that L is epi as well. Therefore, because L is both mono and epi, it's an iso. The same thing works for the equivalence of 1 and 3. So I would like you to do that as an exercise. Now, if there exists an isomorphism from a space V to a space W, we say that V is isomorphic to the vector space W. In algebra in general, when we say that two spaces are isomorphic, it meant to say that they may not be equal, but they are somehow the same in terms of structures. Right? Okay. So if V is isomorphic to W, we write this funny symbol. This relation is actually an equivalence relation among the vector spaces. That meant to say that it's reflexive. Any vector space is isomorphic to itself. To show this, you just consider the identity. The identity is an isomorphism. Just need to think about that. Symmetric. If V is isomorphic to W, then W must be isomorphic to V. Because if V is isomorphic to W, you can find an isomorphism. Yeah? You can find an isomorphism from V to W, call it, they call that phi, and then just consider the inverse of phi. That will be send W back to V. So basically, inverse is an isomorphism from W to V. Transitive, if V is isomorphic to W, so there's an isomorphism over here, and W is isomorphic to U, so there's an isomorphism over here, then according to this theorem, V is isomorphic to U. That is because you could actually take the composition of these two isomorphisms. We know that compositions of isomorphisms is again an isomorphism. So there's an isomorphism from V to U, therefore V is isomorphic to U. Right? Now here we come to the, well, main theorem. One of the main theorems in linear algebra. This tells us that vector spaces are relatively easier to study than any other algebraic spaces. Do you remember in group theory that not because the two groups are of the same size, it doesn't mean that they are isomorphic. For example, there are two groups of order 4, but they are not isomorphic at all. Do you remember the Klein 4 group and the cyclic group Z sub 4? They are not isomorphic, yet they have the same number of elements. In the study of vector spaces, the classification part of vector spaces is relatively easy because, according to this theorem, if V is an n-dimensional vector space over F, it is simply isomorphic to the space Fn. No, if V is a real vector space n-dimensional, for example, it's just isomorphic to Rn. So every vector space of dimension n is simply isomorphic to Fn. See how crazy is that? So you don't need to study any other vector space aside from Fn if you want to study an n-dimensional space. Now Fn will just be enough. And why is that true? What you do is you fix a particular basis for V. No, actually you fix an ordered basis if you want. Remember that if B is a basis, if you get an element V from capital B, you may write V uniquely. It's a linear combination of V1 up to Vn. Unique means that the scalars that you will ever find for this V are unique elements of F. Hence, we may actually form this function. This map phi associates V. So whenever you write V in this manner, unique way of this form, you just simply drop the V's and then just consider the scalars. You put them in a tuple, and that's an element of Fn, right? So we associate this to its coordinate. If you remember, we call this collection of scalars as the coordinate of V. And then the coordinate is an element of Fn. We will prove that this function is basically an isomorphism. So you can think of this as if every vector in your n-dimensional space may be identified with this point in Fn by simply considering its coordinate. This is the coordinate. Yeah, that we claim that this function phi is actually an isomorphism. To prove that, first we prove that it's linear. So we take two vectors u and w from V, being vectors of V, B being as a basis. We can write each one of these as a linear combination uniquely of the VI's, I from 1 to n. And then I'm going to collect these scalars because they will form the coordinates. In other words, as you can see, if I take phi of u plus w, I will add these two sums, it will become this sum. The resulting sum is again a linear combination of the VI's, this being the scalars. Hence, phi of this, by the definition of phi, we collect all these scalars, we put them in a tuple. Like so. That's phi of u plus w. On the other hand, if I take phi of u plus phi of w, I will get this. Now this phi is equal to the coordinate b1, bn. This one equals c1, cn. So when I add these two together, I will also get the previous one. Therefore, it follows that the image of the sum u plus w equals the sum of the images phi of u plus phi of w. The same thing can be done with the other axiom for linearity, that phi of AU is equal to A times phi of U for all A and F. You just use the properties of sums. Okay, therefore phi is linear. Now, to prove that phi is an isomorphism, right, because both of these are n-dimensional, I just need to look at the kernel. I will show that the kernel only has one element in it. Okay? We only need to show that the kernel of phi only has the zero vector in it. So let this v be in the kernel. Because v is again an element of v, you can write it as a linear combination of the vi's. This as the scalars. Okay? So let this be in the kernel. Because that is in the kernel, then of course p of v is the zero vector in the arrival space. The zero vector is this 0. Phi of v, on the other hand, collects the scalars here, place them in a tuple like that, and because this is equal to 0, this is equal to 0. And that follows that each of the AIs, by the way, turned out that they are all just zeros. Therefore, v being this in the kernel, therefore v is actually the zero vector because each of these AIs are, it turned out to be 0. Therefore, it proves that the kernel only has that. So therefore, well, the conclusion before that is that P is 1-to-1. These have the same dimensions, therefore P is also onto, therefore Phi is an isomorphism. Because there's an isomorphism from V to Fn, we can now conclude that V is just isomorphic to Fn. And as a corollary, if you have two vector spaces V and W, both are n-dimensional over F, it turns out that they are just isomorphic to one another. To see this, now this is V and W, right? This is V and W. Take note that they are just isomorphic to Fn by the previous theorem. You can get these isomorphisms. So here you now consider the composition phi2 inverse circle phi1, because phi2 inverse will reverse this, right? If you take the composition, it will become an isomorphism from V to W. Therefore, V and W are isomorphic. Consequently, two finite dimensional vector spaces are isomorphic if and only if their dimensions are equal. So this is very big because it turned out that in linear algebra, the dimensions of the vector spaces will tell you whether they are alike or not. So for example, if you look at the dimension of the space of 2 by 2 real matrices over R, the dimension is 4. Therefore, I know that somehow these 2 by 2 matrices are just or similar to the vector space R4. Why? Because every matrix 2 by 2 is of this form. I can think of this simply as a vector A, B, C, D if I want. Whenever I add two vectors of this form, I simply could add vectors of this form. A matrices of this form, I could simply add two vectors of this form as well. Right? So, the dimension of, well, the space of, what do you call this? This is the space of polynomials of dimension at most n. The dimension is n plus 1 because a basis for that is the set of monomials 1x squared up to x raised to n, right? There are n plus 1 elements in this set, so the dimension is n plus 1. So therefore, the dimension of R, I'm sorry, this is wrong once again, typo. The dimension of Rn square bracket x is n plus 1, therefore Rn square bracket x is simply isomorphic to Rn plus 1. In summary, so this is what we have learned for this lesson. For finite dimensional vector spaces, dimension is the classifying number, meaning to say, if the dimensions are the same, they are just isomorphic. And for a given dimension, we have learned that there is a unique vector space up to isomorphism, namely Fn. Okay? Lahat ng bagay or lahat ng vector space ang dimension ay n, basically isomorphic lang sa Fn. So essentially the same as Fn. Right? So I hope you have learned something new in this video lesson, and see you next lesson.